All right, welcome everyone. We're going to go ahead and get started. Thank you all for coming here. We know you have a lot of great choices for talks, and we really appreciate you spending some time with us today. My name is David Dooling. This is Ryan Richt. We are from Monsanto, which is an agricultural company based in St. Louis, Missouri. But we have operations all over the United States and the world. Today, we are going to be talking about our journey into the cloud, and particularly about the last year, where we really started to take a cloud-first approach. And what do I mean by cloud-first? Well, two things. First, all new development and any significant refactoring of existing applications, the intent is to go to the cloud. And the second is, as we go to the cloud, we want to design in a cloud-first manner. We want to design things so that they are properly architected for the cloud to work within the constraints and the benefits of the cloud. So what can you expect from the session today? We're going to be talking first about what we're calling our theory of the cloud, just some principles that we keep in mind whenever we're designing things, whenever we're doing things, to make sure that we're as successful as can be. And basically, these were aggregated by looking at what people were doing, what was working for them, what wasn't working for them, and collecting those best practices into just a few simple principles that we think really help as we're moving to the cloud. From there, we're going to talk about the infrastructure that we're instantiating and using to run our solutions in AWS. Particularly, it's not going to be any surprise to anyone that we're using a microservices type architecture, and we're using containerized deployments on that. And so this infrastructure is, again, kind of a collection of best practices of how you want to interact with that. And finally, we'll talk about the microservices lifecycle, how we aid and automate development teams in creating microservice projects, developing them, testing them, deploying them, and operating them successfully in the cloud. I also will give you a word of warning. Amazon is a little bit particular about the types of images that they allow you to use in these presentations. And so the stock images that they gave didn't really fit our needs entirely. And so we, mainly Ryan, combined these images in ways that I'm sure their original creators never intended. So you have been warned. Ryan?
Thank you. All right, so who are we and why should you listen to us? I actually first met Dooling back in 2003, so 12 years ago, when we were both at the Genome Sequencing Center at Washington University. And working on projects like the Human Genome Project and the first cancer genome, we actually had petabytes of data and thousands of cores before cloud was a thing, right? Before AWS even existed. So we would really like to think that scientific computing was the original internal cloud. So we've been thinking about these problems for a long time. And now we're both architects at Monsanto, but in reality, what we spend most of our days doing and our background is as developers. So we've each programmed in a large number of languages over the years, but today you'll hear us talking about Scala. And Scala is actually the new backend language standard at Monsanto. And our platform, it's not only written in Scala, but it's made to make it easy to make Scala-based microservices applications. So at Monsanto, we have a little bit of a different challenge. We don't have a single application that we need to scale to 100 million users. Instead, we have thousands of different applications. And we have application development teams all over the world. So not just across the US, but also in Mexico and Buenos Aires and Switzerland. And they all have completely different types of applications. So for instance, we have applications consumer-facing in India, which allow millions of farmers to get agronomic updates and also try to find better prices to sell their crops. But we also have automated seed chippers, which take pieces of seeds, we DNA sequence them, and then ship them all around the world to try to speed up the breeding cycle. We have a robotic automated greenhouse in North Carolina, which takes multi-view hyperspectral images and lots of other measurements of tens of thousands of plants in a very controlled environment. And we also have an Internet of Things platform that takes real-time data from tractors and planters and harvesters all over the world in our field testing pipeline. So the challenge is, how do we get all of these application teams to the cloud in a cohesive manner? And that's why we really want this to have this theory of cloud, because without that, lots of people at Monsanto might think we can just take our existing applications and existing application architecture paradigms and just forklift them into the cloud, right? Do the same thing we've been doing, but do it somewhere else. And in this room, we all know that that doesn't work, right? The cloud is fundamentally different. But it bears sort of writing that down. And we're scientists, right? So we think about this as, what is the theory of cloud? Can we write down what makes the cloud fundamentally different? And if we do that, what can that tell us about challenges and opportunities in the cloud? And thus, what is the optimal sort of cloud architecture? And there are lots of different topics that we could talk about, but we really think these 5 are the most important differentiators of the cloud versus internal. The first is that the cloud is highly automated, so we have software-defined everything. And that's very different from our internal data center, where we have teams of people racking servers and swapping out hard drives. And what's really interesting we'll talk about is that software is special. Second, instead of making upfront capital investments, we have the elastic nature of the cloud, so this combination of potentially unlimited scale, but also a pay-as-you-go expense model. Next, we have the ability to create highly available applications because we can have multi-server, multi-AZ, multi-region deployments and shards and replicas and all of that good stuff, right? Really interestingly, it's really a do-over for security in the cloud. We get to start from scratch to create a secure environment, and we'll talk about how we think about doing that from first principles. And lastly, really orthogonal to elasticity and availability is horizontal scalability. We have the ability to provision more like things at any time, so our applications need to take advantage of that. All right, so given that that's the way the cloud is different, what should we do about it? So we'll talk briefly about each of these. Because the cloud is automated and software is special, what we should be doing is creating higher order automation. So not just first-level automation or using the APIs that Amazon has, but building automation on top of automation. Second, there's lots of reasons elasticity is valuable, but we think the most important one is not just taking advantage of it in a first-order way, but completely re-architecting how we do application lifecycle. For highly available, we get to deploy lots of copies of things, right? But that doesn't actually make our systems fault tolerant. And architecting applications for fault tolerance is very different. Security, we'll talk about what we call security by construction, sort of this idea we've stolen from functional programming. And then lastly, we have the ability to make things horizontally scalable, but what does that really mean? And how do we make parallel systems out of commodity hardware? So first, really, what I hope you take away from this talk and what all of the practice parts Dueling is going to talk about are about what we call higher order automation, or colloquially, robots building robots at Monsanto. So we think automation is not good enough, right? We could have some configuration files or some simple language that creates stands up infrastructure in an automated way. But the real opportunity is that software is special. Once we bring something from configuration into software, we can write higher order software that generates that software or automates it in another way. And then we can stack more and more layers of automation on top of that automation. So the ante of this game is clearly, you have to have automated tests and continuous integration and continuous delivery. But we really want to set the goal as we don't want this automated pipeline to terminate and someone getting an alert. Like, we have all this automation, and then like, hey, you need to go push this button or remediate something. We want the system to be able to consume that data that it creates and self-heal. And we also want to build automated tools that help us to make more automation. And so Dueling will talk extensively about what we've done in that area. On the fault tolerance side, our application teams today, for good reason, make a lot of assumptions about how they build applications. And so with apologies to Peter Deutsch, some of those are things like the hardware is reliable, the network is reliable, the database is reliable, and that all the other services are available, and we live in this magical kingdom where everything is secure because it's inside the VPC, right? And at Monsanto, internally, we spend a lot of money on very expensive hardware and teams of people to preserve this illusion that things are infallible, right? But obviously, that's not what we're going to do in the cloud. So we need to build applications differently. But first-generation cloud paradigms knew that these were problems. They tried to solve some of them, but they tried to push all of that effort onto the application developer. So I'm sure you've seen platforms that are like, everything is stateless, everything is idempotent. But in reality, the world is not stateless and idempotent, right? And so we think that we can do better. Should all of these federated application teams across the globe from Monsanto, should they all have to say like, oh, I should do retries, and if I do retries, I should do exponential backoff so that I don't create more contention. And when I do that, should I need to add normally distributed random noise jitter into my exponential backoff? Like, no, right? Those are things we should put into the platform, along with things like, if your first generation cloud platform assumes everything is stateless, it can just blow containers away when it wants to make any changes. But we would actually like to take the effort to preserve in-flight transactions and do the best we can in a second generation cloud platform. And when we were looking at the cloud first at Monsanto, we did the cost calculation and we said it's going to be more expensive for us to run in AWS than on-prem. And actually, now we think the opposite. And it's because elasticity doesn't just give us this first-order result of, oh, I don't have to build for peak. I can have some basal level of capacity and then scale up dynamically with load. Sure, that's valuable. But what we think is really the most valuable is this redesign of the application development paradigm. So at Monsanto, we typically have dev, prod, test, post-prod, and some other environment I can't even remember the name of, static environments that we keep up all the time, most of which are not being used at any point in time, right? So what we really want to get to in the cloud is what we call ephemeral environments. If we have enough automation that we can just stand up a VPC from scratch, then I can run any kind of tests or present to my customers an early version of the software and then blow that away instead of keeping 5 static environments up all the time for everything. And secondarily, Monsanto is a science-based company. We're built on science and innovation. And the cloud really reduces the transaction costs for people to do experiments. Internally, in Monsanto, if you want a virtual machine, you can give us a couple $1,000s and wait a couple weeks, and then you get one, right? But those transaction costs go to 0 in the cloud. So we need to make sure that we put automated and self-service systems in place that we can pass those benefits along to our developers. OK, so the really exciting one. We also were slow to get to the cloud because we thought the cloud is going to be less secure. Is it secure enough for our data? And now at Monsanto, we have the exact opposite conversation. We say, we know we can make the cloud more secure than we could ever possibly hope to have our internal environment remediated, right? And since we get to do it from scratch in this do-over, in functional programming, we have immutable data and immutable variables, right? You can never reassign things. So we have this concept called correct by construction, meaning when I new up an object, it has to be perfectly realized, it's perfectly consistent, because I don't ever get to change it, right? So we want to do the same thing with security. Is it possible to create a level of security automation where it's not even possible to express insecure constructs? Can we use the type checker and sort of generation time checks to only allow you to create constructs which are secure? And Dueling will talk about that. So lastly, on the theory side, we have horizontally scalable. And we think this is really orthogonal from fault tolerance. So those systems like that are based on Paxos or Raft, they kind of give this illusion of having a distributed system. But the problem is they don't actually scale control. They scale everything but control. So we really encourage everyone to go back, and it's not a coincidence that this paper is from Amazon, the original Dynamo paper, that this should really be the gold standard of what a distributed system means. And that scales out both reads and writes, which means things like you can't have the master-slave paradigm. That you can take out any node and continue to provide scalability, so you can't have one coordinator and 100 worker nodes. That doesn't work either. But a way to formalize this is to say the overhead costs has to be at most increased constantly when you add another node, so that the growth is linear. And only eventually consistent systems like Dynamo, so sort of AP systems in the CAP theory, have those properties. And that imposes new challenges to application developers in that all applications now have to realize that there can be multiple inconsistent states of the world, and they have to merge that data and commit it back. And that's a major change for applications. So that's enough theory. I'm going to turn it over to David to talk about our practice.
Thanks. So as Ryan said, we are very aggressive about automation. And in particular, one of the things that we want to automate is infrastructure. And so why are we interested really in automating infrastructure? Ryan talked a bit about it, but what does that really mean on paper? Well, we want each of our development teams to be able to move at their own pace. We don't want them to have to wait for someone else to instantiate a virtual machine or stand up a database for them, or to have to coordinate with other teams around shared library updates or framework updates or anything like that. We want them to be able to manage their infrastructure in an easy, good way, and we want them to operate in a true DevOps model, where not only do they own their stack, their solution vertically, but they also own it from cradle to grave, from creation to retirement, right? And so we want them to be in total control of how they're moving forward. And to do that in a good way, in a secure way, in a way that really addresses all of those principles, all the theory of cloud that Ryan talked about, we need to automate things because we can't distribute expertise in every aspect of highly available, fault-tolerant, secure computing to everyone instantaneously without something like a lot of automation. So what does it look like, and how do we begin to automate the instantiation of hundreds or even thousands of VPCs? Well, first, let's look at the architecture that we want to create. And as I mentioned earlier, this architecture is going to look, this diagram is going to look very similar to diagrams that you've seen probably seen in other talks here at reInvent, because it is really just an aggregation of best practices of what people are doing to deploy and manage microservices using Docker containers in AWS. But before I get into the details of each part of this, and we'll do that in the next couple slides where it's not quite so overwhelming, I do want to say a little bit about how we approach consuming AWS services. Initially there was some concern, well, we don't want to get locked in with AWS. But we pushed back pretty hard against that idea, because really what we don't want to do is re-engineer everything AWS has already engineered. That's going to take a lot more resources and a lot more time than some speculative time in the future where we may need to move from one infrastructure as a service provider to another. And so we are very aggressive about using native AWS services where we can and where it makes sense. So again, this VPC, this design for microservices is pretty standard. First, we stand up a VPC, a virtual private cloud, our own virtual IP space in the cloud. And we span that across 2 availability zones in a single region at present, although we're planning to use 3 availability zones and eventually expand to multi-region type deployments through automation. Looking at the far left portion of this slide, we have the 2 public subnets, one in each availability zone, and that's where our public assets are. In each of those subnets, there is a network address translation instance, or NAT instance, and all of the egress, network traffic egress from the private subnets out to the larger internet go through those NAT boxes, and we have IP table rules on those NAT boxes to log all that traffic so that we can collect it and analyze it later. There's also a Bastion instance, and that's the only SSH ingress point for the VPC. If you need to get to any other host, you have to bounce through that Bastion host. And then the last in the public subnet are our Elastic load balancers, and we have one for web traffic and one for our services traffic. And those ELBs sit in front of our gateway auto-scaling group. So in the private subnets, again, one in each availability zone, we have an auto-scaling group for gateway services. And so that's in the middle of the unshaded area right there. And on each instance in our gateway auto-scaling group, we're running a web gateway and an API gateway. Our web gateway is Nginx, and that is essentially communicating with our single sign-on provider and fronting static assets in S3. So just HTML, CSS, images, and JavaScript. That's all that's coming from there. So static, single-page type loading paradigm. And our API gateway is Akana's network director. And that is sitting in front of our services that we actually deploy into the service auto-scaling group, which is just to the right of that on the diagram. And that's where the actual code, the actual Docker containers generated from the code that our solution teams are creating get deployed. The last thing in the private subnets is our logging and metrics instance. And for those, we're using ELK for the Elasticsearch, Logstash, and Kibana for our log sync. And we're using Prometheus for metric scraping of our services. And the Kibana dashboard and PromDash are available also through the web gateway, so people can access them from outside the VPC developers. And so finally, when you're running these services, you need to persist your data, and for that, we're using Postgres RDS. We really feel like PostgreSQL is the best kept secret in relational databases. It's an awesome product. It has great features, and it's just rock solid. We really love it, and we especially love it in RDS. And then we finally glue all this stuff together with things like S3, EBS, IAM. We use a lot of Route 53, both internally into the VPC and for external DNS. And then monitor everything with CloudWatch and CloudTrail. So this is what it looks like all together. And just to give people a flavor for how packets kind of flow through this system, we'll just sort of walk through a simple request. So let's say you give the host name for your endpoint that you've registered in Amazon Route 53 for the web ELB to somebody. They type that into their browser. What happens? That browser is going to do a DNS lookup. It's going to get a CNAME for the web ELB. That's going to resolve to one of the IP addresses that are associated with that ELB, and it's going to send the request. That's going to pass through the web ELB on to the gateway layer, and specifically an Nginx container running in the gateway layer. Nginx is going to say, you're hitting me with HTTP on port 80. I'm going to redirect you to port 443 so we can do secure communication. That goes back out to the browser. The browser sends the new request in over HTTPS. That hits the ELB again, hits the Nginx gateway again. Nginx checks to see if you have an authenticated user in your, that token in your headers. You don't, so it redirects you to our single sign-on solution. You type in your username and password. It bounces you back again through the ELB, through the Nginx. The Nginx says, good, you got the header, you're on port 443. I'm going to proxy you to the S3 bucket that is serving the content for this site. From there, you're grabbing the HTML, the CSS, the images, and the JavaScript. The browser starts to render that page. It hits some JavaScript, starts to execute it, and makes a service call. That's going to hit the service ELB. That's going to go to our API gateway. The API is going to make sure it's a valid request and that it's an authenticated request. And then it's going to pass it on to the service layer, specifically one of the nodes in the service auto-scaling group that is running the service that you're calling. That service is going to do what it does, either read or write some data to Postgres, and then respond going out. And so that's sort of how the request cycle looks in this infrastructure. And I should also mention we're flexible about how we configure RDS in this environment. Each microservice, as you would expect, has its own user and schema in the database that it solely controls and it solely accesses. But if you're concerned about cost, you can multiplex multiple schemas for multiple microservices onto a single RDS instance. If you're more concerned about performance, then you can have multiple RDS instances and have just one of each for each microservice. So you can imagine to instantiate an infrastructure like this could take dozens or even hundreds of API calls to AWS, or you could use just one, specifically a call to the AWS CloudFormation API. And if you're not familiar with CloudFormation, it's basically a way for you to define what resources you want, what are their relationships, hand that to Amazon, and with one API call, create stack, it creates those sets of resources, which it calls a stack. And the way that you define those resources is with a template, which is just a big blob of JSON. And on the right-hand side of this slide, we see a small snippet of what CloudFormation template JSON looks like. At the very top, we're creating an elastic IP address. That's that type AWS EC2 EIP, elastic IP address. We give it a name at the top, IP address, and then give some properties to it. We create a security group right below that. That's that AWS EC2 security group, whose name is Instance Security Group. And then at the bottom, we actually create an EC2 instance that we call Web Server Instance. And it's not shown, but those would be associated with the security group and with the IP address eventually. So we really like CloudFormation. It's a great way to instantiate arbitrarily complex infrastructures with a single call. But we have found that it has two weaknesses. First, it doesn't create a good way for you to create templates from scratch, at least complicated templates from scratch. There are things like CloudFormer and the recently announced CloudFormation Designer, but those are very manual processes. Manual processes are error-prone. We want to automate things. We want to think about things at a higher order than that. The second weakness is CloudFormation doesn't give you any real way to interact with that stack, interact with those resources that you've created once you've spun it up. And so those are two areas that we thought we could improve upon. So talking first now about creating templates from scratch and doing that in a good way, the template to create this infrastructure is more than 5,000 lines of JSON. And if you've ever edited JSON by hand, you know that you don't want to edit a 5,000-line JSON file. We started doing this initially when we used CloudFormation, and you're always forgetting a comma somewhere or not closing a double quote somewhere, and it just became a real problem. And so we started to look around for tools that would help us to create CloudFormation templates in a better way. And there were a few out there that solved this problem, that invalid JSON. But there were other problems that we would hit relatively frequently that they didn't solve. And so we created what we call the CloudFormation template generator. It's not the most original name in the world, but it does give the point across. Plus, we tried a bunch of other names, and they were already taken. So what is the CloudFormation template generator? As its GitHub page says, it's a type-safe Scala DSL, or domain-specific language, for generating CloudFormation templates. And the URL for the GitHub page is right down there at the bottom, and we'll have those at the end too. But what does that mean, a type-safe Scala DSL for generating CloudFormation templates? Well, it certainly solves the problem of creating valid JSON, just like the other ones. But there are other problems that it solves that the other template generators don't. For example, referential integrity. So we can just look at an example and walk through to say what we mean by referential integrity. In the top right orange box there, we're creating a RDS database subnet group. You can see that at the bottom there where it says type is AWS RDS DB subnet group. And at the top, you're giving it a name, DB subnet group, and then you're listing some properties for it. You're defining properties for it. And the key property for a database subnet group is that subnet ID section, the actual subnets that are part of the group. And here you can see these are references to other entities in the template, specifically DB subnet 1 and DB subnet 2. Now, the other template generators make no attempt to ensure that those references are in any way valid, that those things actually exist elsewhere in the template. Our DSL, the CloudFormation template generator, does that. What's more, looking at the code at the bottom, which is actually the DSL for generating it, you can see that it's fairly similar. It has a lot of the same things. You give it a name. You have a thing called subnet IDs and DB subnet group description, just like you have above. But you can see it's more compact, it's simpler, and it also, in addition to making sure that those subnet IDs that are resource refed in that sequence, not only do they exist, but they make sure that they are the right type of thing. Because even CloudFormation's built-in template generator makes no attempt to ensure that something you are referencing is of the right type. So you could submit a template that had in the subnet IDs an EC2 instance reference, or an ELB reference, or whatever. And it would pass the validator for CloudFormation. It won't pass ours. You try to do that with ours, it'll say, that's not a subnet, I'm not creating this template. So instead of you instantiating some stack, having it start spinning up things, having it start costing you money, only to have it all roll back, still get charged for the whole hour though, we prevent that from happening before it even starts. And as you can tell, it's also less code. And less code means less chances for error. Now, before I go to the next slide, please do not try to read it, okay? You'll hurt yourself. So we only have these examples here to show just sort of relative amounts of complexity, because another thing that we found when we were creating these templates, sort of using the DSL, we went from 5,000 lines of JSON to 3,000 lines of Scala, but it's still pretty long and still pretty cumbersome. And we found that we did a lot of things over and over, a lot of the same sorts of things. There was a lot of boilerplate involved in a lot of things. For example, here, the 2 orange boxes represent the CloudFormation template for an auto-scaling group and its associated launch config. That's a one-to-one correspondence that's always there. And so you need to make sure that those are referencing each other properly and you have all the boilerplate and stuff like that. And we thought, we can do better. We can create higher order builder functions. In this case, ASG for auto scaling group, wherein in one function call, you're creating both the auto scaling group and its associated launch config, and behind the scenes, it's getting rid of boilerplate, it's filling that in for you, and it's making sure that those things are associated properly. So we've created these higher order builders for things like auto scaling groups, ELBs associated with auto scaling groups, EC2 instances, stuff like that. So then we were able to get 5,000 lines of JSON down to about 2,000 lines of JSON, of Scala. And from there, we looked at what was left and found that it was mostly related to security groups. And so Ryan and I talked back and forth and tried to figure out, what could we do to further shrink our chances for error, reduce the amount of code we have to create these templates. We settled on essentially automatically instantiating empty security groups for every resource that can be associated with them. So ELBs, RDSs, EC2 instances, they automatically, when you create them, they automatically get a security group associated with them. And the nice thing about CloudFormation is that you can create these empty security groups, and then later or elsewhere in the template, you can add ingress and egress rules to them sort of separately. And so we did that, and then Ryan took it one step further. He said, how can we make these things easier to read? And again, don't read the JSON. It is bad for your health, okay? But go ahead and read the top part. That's the DSL. Ryan created the chicken foot operator, which basically tells you, what is allowed to go where. It's really easy to read. So you can see that the Bastion host is allowed on port 5000 to access the ELK box. Same for NAT1 and NAT2. They can all access the ELK box on port 5000. So the ELK box has an ingress rule from those 3 things that allow on port 5000, and that's where Logstash happens to be listening for syslog messages, right? And so you see with these 5 simple, easy to write, easy to read, easy to understand lines, you get these 7 security groups, ingress rules, that are not easy to read, not easy to understand, and they're just a pain, and they're easy to mess up. And if you have a security organization like ours that wants to be able to inspect your security groups and ingress rules and all that sort of stuff in the templates you're instantiating, you better believe that when you go to them with something like in that top box, they like it a lot more and it goes a lot more quickly, that review, than the stuff in the bottom box. So that kind of covers the CloudFormation template generator and what our solution for creating better templates, more reliable templates. So what about interacting with the stacks, those CloudFormation resources once they're created? For that, we created Stacks, S-T-A-X, and its GitHub URL is at the bottom. It's just Monsanto code/stacks, and it's what we use to create and manage CloudFormation templates in AWS. And there's a lot of commands, and we're not going to go through all of them, but the documentation, the README on that site is really good. Encourage you all to check it out. But basically, it allows you to do what you would think. You can create stacks, you can delete stacks, but you can also manage the RDS instances. You can spin up new ones and get rid of old ones inside that VPC that you create. You can also do, if you're running in production and you want to turn off the Bastion, it can do that for you with the sleep call. It can validate templates for you as well, and various other things. And another nice thing that we'll talk about as well is it will allow you to SSH into the stack once it's created. So what actually happens when you call stacks create? Is it just calling CloudFormation create stack? No, because that wouldn't help you very much, right? Because if you've ever used CloudFormation, you know that there's no facility for CloudFormation to create EC2 SSH keys. And if you think about it, it makes sense, because Amazon does not store them for you. The only time you can retrieve them is when you create them, because they don't keep them. And so if you created one inside a CloudFormation template, there'd be no way to actually get the private key, so it would be completely worthless to you. So stacks, in addition to creating random names for things, for the templates that for the stacks that it's creating, it validates the parameter file, it validates the template file, but it also generates a custom key pair, SSH key pair for that stack, and then saves the private key so you can access that stack later. It also creates an S3 bucket for the stack, so that any assets that the resources in that stack, in that template need, can be uploaded to them for them to download once they're created. For example, our NAT boxes monitor each other to see if they're alive. And if they sense that one is dead, they take over its route. They update the route table and then restart the other one, so when it comes up, it can take back over its route. So that we don't get a lot of bloat in our user data for our EC2 instances, we can just put that script up in that S3 bucket, and they can download it from there with the appropriate Amazon IAM role for EC2 instances with that. So once all that's done, then it actually creates the stack. And that template that we saw earlier, it takes about 10 minutes to create. Once it's created, you can just call stacks connect, and it automatically queries AWS for all the IP addresses and everything that it needs. It already has that private key, and it spits out, it saves off an SSH configuration that also automatically allows you to jump through the bastion host to get at the other hosts in the stack. And it does that in a secure way by forwarding your SSH agent, so you never have to put your private key into AWS at all. It's always just on your local machine, and you can get to any instance inside that to poke around, which is really helpful when you're debugging and developing things. We really like stacks, but it's not as safe as it could be. Because while, in the letter of the law, it adheres to the principle of least privilege. That is, no one in the organization should have permissions to do things other than what is required for their job. And since we want developers to be able to instantiate infrastructure, we want them to have those permissions. It kind of violates the spirit of it, because to stand up a stack like the ones that we've talked about in this talk basically requires root access to your AWS account, because it's spinning up all different kinds of resources, it's creating IAM roles and users and all that sort of stuff. And so while it strictly adheres to the principle of least privilege, in spirit, it basically forces you to give all of your developers the keys to the kingdom in AWS. And so we thought about, how can we improve upon that? How can we still give developers what they need without, being completely insecure? And so, we went for higher order automation, right? So this is the theme, right? So Amazon has automated infrastructure with AWS. They automated AWS with CloudFormation. We automated CloudFormation with stacks, and now we are automating stacks with stacks as a service. Okay, so now the stacks as a service needs to have permission to create that template, but developers just need to be able to authenticate themselves as a developer in Monsanto and then call stacks as a service. And here we have a web UI for stacks as a service that we've created, but it's all API driven, and we've actually ported stacks to use the API on the back end now, so that that CLI avenue is still available to you should you want it. And so here's the screenshot for sort of the create page. You select a template, and then you give information for your tags and your input parameters for your template. And you might be looking at this and saying, let's see, you're managing CloudFormation templates and sort of allowing people to stand them up with someone else's credentials. That sounds a lot like the AWS Service Catalog. And you're right, it does sound a lot like that, except ours came first, it has a better UI and an API. So you can also do things like list. So you can list all the currently running stacks that are in your account. You can click on one of those, drill down, and get information about tags and the outputs, all that sort of stuff. And what's more, because we have more intimate knowledge of what's going on and what we're doing inside of that stack, we can drill down even further and say, you know, we expect etcd to be running on every host. We can interrogate and make sure that it is, you know, and all the other services that we know should be running in a stack, we can provide you information on that as well. So we have about 15 minutes left. We're about 40 minutes into the talk. So it's probably a good time to take stock of where we are and what we're doing, right? We're throwing a lot of information at you. I hope it's helpful to you so far. But remember, we have a very diverse and distributed IT organization, and we want all of them to be able to move at their own speed. And so we really want to automate as much as we can, and we want to give them as much independence as they can. That's why we are so aggressive around automating the infrastructure. And it's also one of the driving motivations for why people choose microservices. You want each of those microservices to be able to evolve at its own pace. And so Ryan is going to talk to us a bit more about our approach to microservices.
All right. Yeah, so now that all the infrastructure stuff is automated, what can we do at the application level? Because that's what I really care about. So in case you're not familiar with microservices, the meme at Monsanto, at least, is cupcakes, not wedding cakes, where a wedding cake is like your traditional multi-tier application that has lots of functionality, and it all shares the same database, right? And microservices are meant to deliver on the broken promises of things like SOA, or even like Smalltalk-style objects, in that we can build systems that are truly independent because we impose this extra constraint, and that constraint is that they all have their own database, and no one is allowed to talk to anyone else's database. You have to go through the API. So we're asking developers to build microservices. The problem is, we used to say, oh, you know, for every project you make your one wedding cake, and now we're like, make 200 separate microservices. That's a lot of overhead. Like, we've just blown up the overhead of making new projects, right? Even for a small project, we have like 10 microservices in that project. So clearly we need some automation. And just to sort of motivate why we're doing this all in Scala again, because this is going to be about Scala microservices, there's really two reasons. The first is that we have these advanced abstractions. So if you were to make a list of all of the modern stuff that's been invented in programming languages in the last 20 years, things like algebraic data types, enforced immutability, destructuring, pattern matching, and then type classes and high performance asynchronicity, there's not very many languages that can check all of those boxes. It's basically Scala and Haskell is what we came up with. And since we are historically a JVM shop and there are more Scala developers, that tilted us in that direction. But really, what drives us to Scala is these advanced type constraints. So the features that David Dooling showed you about CloudFormation template generator, you don't have to know about any of this or see. But the way that it works is with things like f-bounded polymorphism and these sort of advanced generics and type projections and things that we have in Scala. Things that Java will never have, right? Java 8 has lambdas, hooray. But it doesn't have these sorts of features, and we use those extensively in CloudFormation template generator, for instance, in all of our libraries. It's worth noting, I guess, that when you try to new up something that doesn't have that referential transparency, we don't give you an error that it's not true. It doesn't even compile. We enforce at compile time you can't even write to a CloudFormation template that's incorrect. So anyway, on the application side, we want to provide some automation to make it easy for people to make lots of microservices very rapidly. So we have another service called Project as a Service, which generates new projects for you. And its schematic outline looks kind of like this. So you hit the service. We create a new private GitHub repository for you. We check out a template and templatize it with some values. We check it back in as your first check-in. We set up a series of Jenkins jobs that do continuous integration and continuous deployment. Package those up in Docker containers, push them to our private registry. We auto blue-green deploy that into production. And then when your service gets deployed, we provide it with things like dynamic service discovery, sort of inspired by Nerve and Synapse from Airbnb, where you can just connect a local host for any other service and you get it. And also with automated logging and metrics, again with Elk and Prometheus. And of course, there's a web app that you can literally use on your phone, which is a form, and it has a big red create button with gratuitous like ponies and corn, success animations. Because why not? So we don't want to manage source code repositories, so we actually use github.com hosted private repos. And really, we don't just want to have a source code repository. We need some semblance of project management. And we actually really like GitHub issues. So when we create your repository, you also get a wiki and you get GitHub issues, which we use extensively now in place of other solutions that have too many features. Really, the work, though, of project as a service went into what we call the simple service template, which is, it's about as simple as like SBT is the simple Scala tool, a build tool, which is to say it's not simple at all, unfortunately. But it really provides this suite of best practices for our developers. So in that template, we do things like we stand up an ACA actor system, so it's obviously completely async and non-blocking. We use a spray, which is an application container-free runtime for creating RESTful services, and we show you how to set that up and provide some basic endpoints. We also have integration with Scala test and the ACA and spray test kits to show you how to test with and without a web server, with and without a database. We instrument that template with these administrative REST endpoints that we'll talk about in a second. And we also inject these logging and metric capabilities into that service, so you can just use them. The template also provides the logic to do our automatic Dockerization. And since we're supporting Postgres, we also spit out a Vagrant file that has a Postgres Docker container running in it so that you can have a local development environment. So then whenever you do a check-in, we test and build in Jenkins. So we programmatically obviously set all those jobs up. And then we have a standard endpoint to create minimal Docker containers. So we have a minimal Debian JVM, OpenJDK, I think, Docker container that those projects get injected into. And what's really interesting is we don't stop there, right? We don't just like push your container to our repository, because we know when you created your microservice which stack that it belongs to, and we have all that information in stacks. So we actually do blue-green deployments into stacks for you. And the first time that you create a service, we automatically register it with our API gateway, which is Akana right now, which provides a catalog of services for all of our developers, and it also handles things like OAuth and CORS, and so we set all of that up automatically upon project creation as well. And I want to just briefly run through how we do our blue-green deployments. This pattern might look familiar, but it took us a long time to get it right. We started with lots of solutions that were terrible and didn't work at all. And several of these components are also available on our open source repository on GitHub. And if there's anything that's not open source that you want, let us know. So this setup in the square with the router, fleet, etcd, and these two Docker containers, registrator and route updater, this exists on every host in that services auto-scaling group that Dueling was talking about earlier. So as you would expect, you make a commit to GitHub. That notifies over the hook to Jenkins, which is going to build your code. And assuming it passes, it's going to create that Docker container and push it to our private Docker registry, which I'm really excited that we don't have to run a box to do that anymore. But what's interesting is then we look in etcd to say, does this service exist at all yet? And we use kind of the auto-incrementing build numbers from Jenkins as a source of revisions, like versions. So they're always increasing. So it doesn't exist, so we're going to put a key, a pointer from service 1 to revision 1 into etcd. And we're going to ask, we use fleet to schedule our services. So fleet's then going to deploy that container on some random host in the auto-scaling group on some random port, and the port is obviously the complicated part. We use an open source tool called Registrator, which it basically spies on Docker events. And so it's going to notice that this Docker container was deployed somewhere, and it automatically updates etcd to say this list of hosts for service version 1, revision 1, it exists at this host and this port. So now if you were to make a request from the outside world or from the inside world, it would go to this router, which originally we had this Nginx thing, but it turned out we wanted tighter integration with etcd and with caching and things like that. So this is another Scala spray application, fully async, blah, blah, and it's available open source. It will redirect you to the container that you would expect by looking it up. But the interesting part, right, is if you push another revision, things go well, it gets pushed to the registry, but it notices a service 1 already exists, so it's not going to touch that. It's not going to touch that pointer. We're going to ask Fleet to schedule it. Fleet's going to schedule it somewhere. Registrator's going to notice, and it's going to say, hey, service 1 revision 2 is running on this list of hosts at these ports. And if you were to make a request right now, you still get the original version. Unless you pass a magical header for testing purposes, you can get the other version. OK, but the cool part is that we have this container we wrote called route updater. And what it does, it periodically looks through the keys that are in etcd to see if there's a newer revision deployed of anything that's already been running. So here, revision 2 is actually newer than 1. So it will first call this administrative endpoint smoke test to make sure that your system is up. You might want to check, like, oh, is my database up, or whatever. Is my actor system up is kind of the default. And if so, it'll update that pointer. And so now new traffic is going to go to the new container, but in-flight transactions to the old container are going to continue to be processed until route updater asks it to shut down. And then it's given time to sort of gracefully finish processing all of those transactions, at which point the actor system will be shut down, which means the container will be shut down. And registrator will eventually notice that and garbage collect service 1 revision 1 out of etcd. So it's kind of simple, but we try to make separate components, and we used a lot of other different strategies that didn't work very well, but we really like this one. So lastly, the operational aspects of the microservices, we have both logging and metrics. So obviously we have logs of all the things, right? Service container, CoreOS, Bash and ELB, and we use standard open source tools to do that. What's more interesting is that we're using standard Scala logging, and we're writing to elk. But originally, the recommendation is dump all of your logs to standard out and use the Docker mechanisms to collect them. Well, that doesn't work very well for JVM applications, right? Think of the one log I really want is the stack trace. I need the stack traces when things explode, and it's a multi-line thing, right? So why should I dump that to standard out and try to glue it back together? We actually log everything as structured JSON blobs because we have the luxury of doing that at the application level. And we were using Logspout, and we actually wrote a system instead to write directly to elk, and that seemed to be more reliable. And lastly, because we're doing this automatically, we can inject things like the container ID and GitHub check-in into every log message as a metadata field in those structured JSON blobs. And then lastly, we want metrics. So we're using Kamon and Prometheus. Prometheus is really cool. Unfortunately, it's not supported by Kamon. So we had to write an exporter that preserves those sort of deep structures of Kamon and gives them to Prometheus. And you can have, that's open source at Spray Kamon metrics. And we also have improved tracing. And then lastly, Prometheus is cool, but it's not made to be automated, of course. So we forked all of their containers to make new containers that automatically write the configuration files by querying etcd. You can't make dashboards programmatically, so we inject SQL statements into Prometheus's database to set you up with default dashboards as soon as it creates itself. We have CloudFormation template generator code to do all this on EC2, EBS, RDS. And then Prometheus didn't support simple notification service, so we contributed a patch to do that from Prometheus as well. So the little time remaining.
So yeah, we'll just go quickly through where we see this platform going. Thanks for sticking with us this long. I mentioned, before I sort of get into the details of this, I just want to say, one of the other principles that we have about the code rewrite is that everything is disposable. We want to maintain as little code as possible. That's why we want to consume native AWS services. That's why we're aggressive about using open source software. That's why we're aggressive about open sourcing our software. We get PRs from other people for our CloudFormation template generator, and that's great. And so when we see something like AWS Service Catalog, when it has an API, you better believe we're going to jump on it. You may have been wondering, why are they doing CoreOS and Docker? Why aren't they using the EC2 container service? It really wasn't around when we started, but we are going to do that aggressively in the future. We'd love to have some new features from AWS around IAM so that containers can have roles and that we can restrict RDS roles to VPCs. We're going to look at the API gateway. We'd like to get rid of our NAT boxes and use the VPC flow logs natively when they have CloudFormation support. And we also want to invert our control for deployment so that instead of a central Jenkins having all the logic, the VPCs themselves know what should be deployed there, and they can query the Docker registry. And then we'd like a little more predictability around CloudFormation template generators. So please do take away higher order automation, robots not killing robots, robots making robots. Either way, chaos monkey. And because we really feel like putting hands in the tools of developers lets them spend more time servicing their customers and innovating than worrying about stuff that's non-differentiating. These are the folks that did all the work. We have a great team. We've come a long way in a year. Thank you all for sticking with us. We know it's a lot of information. You can find more information at engineering.monsanto.com. Remember your evaluations. Check out our colleagues' IoT presentation tomorrow morning, 10:15 in Delfino 4005. Good stuff, building on what was there today.
And if you want a job writing Scala, even if it's remotely and you don't want to move to St. Louis, contact us and download our open source stuff. So thank you.
Thanks.